Okay, let's wait a few more minutes, 1-2 minutes, and then we'll start. There. You start the masters after COVID, right? Or right, you're the lucky ones. How has it been so far? Better than expected, or you're literally in a pivotal moment. Like, I would not expect it really with ChatGPT, like really changing the landscape. I can tell you that much. It's a second renaissance. That doesn't happen easily or often. So I think like also in the masters, like I don't know if it's like this year or next year, or but a lot of courses will be ChatGPT. Well, not focused necessarily, but you know, like of course they will absorb the knowledge and experience. Okay, but like maybe we should just start. Yeah. All right. Well, welcome all. Thanks for attending. In this module, I know in the Canvas it's has a bit more complex name, generative models and diffusion models. But okay, diffusion models are basically generative models. I just wanted to back then emphasize that we're going to be talking about that as well, compared to previous years. But okay, maybe I'll just simplify to the generative models, and that's it. Well, thanks again for coming. In this module, we're going to discuss about, describe the generative models. What is, perhaps you had some discussion about in the introduction lecture from Eric and Christos regarding the structure of the course. Do you have any questions about the course? If you have any confusions, please send us an email. It is an effort to basically teach you all basically about state-of-the-art AI. Typically in master programs, you don't really teach state-of-the-art cutting-edge stuff because, well, it's cutting edge. You know, like there is no time to actually absorb it. It's also like it's not mature enough to be taught. However, it's also a pity, right? Because it reflects the latest of the latest and the hottest of the hottest, and of course we're all interested into what, you know, what's the hottest right now and what's really there, especially in AI. So this course serves this purpose. Of course, this comes with a few problems. I could have taught everything, but I'm not an expert in everything. However, we have very good, very strong experts in like a lot of different areas. So we invite people to teach, but having multiple people teaching at the same time, this creates problems sometimes, or confusions and whatnot. So yeah, if there is any unclarity at any point, please send an email as soon as possible. Regarding the exams, there will be an official announcement, but well, there was a lot of back and forth because last year students felt that the course was a bit too, let's say, unclear regarding examination, because we were using the project and whatnot, and you're like, okay, grading projects is also always hard. People complain, you know, like, well, okay, why you know this or that. Then we had the exam. They asked for an exam. I had the exam. Well, this year students also complained, so the conclusion is that you always complain. Not you, like people complain always. But that's okay. It's a fair point, because there was also the point that okay, masters should not be just about exams, but also about doing a project and like doing it as best as possible, even if it's less clear how to examine it. But we still wanted to make some improvement. So compared to last year, we're gonna have oral assessment of the project. So we're gonna invite the teams for half an hour and then discuss, and then also discuss with each person, so that we can also make it like the grading individual, which is one of the regulations. Okay, So this is more or less about the course and the structure, very briefly. About the details, I guess Eric and Christos already told you about this. Do you have any questions about, otherwise, yes?
So about the essay, it says that it should contain then the what we've learned from the project and kind of make it intertwined with the modules that we took.
Yeah.
Can we say ourselves which models we took, or we have to base it on the modules we're assigned to? Because like in reality, we can really take any module we want, right?
Yeah. Well, that's a good point. So not to create more confusion, I mean that's a relevant question. Let me discuss this with the rest. How would we go about it? And my perspective is that, look, I want to treat you like adults, right? Like, I really want that. It's not always easy for, like, also from my perspective, like my side, like I do mistakes or whatever, like I have limited time, but also from your side, you know, like we have to satisfy a lot of different people. Well, not satisfy, but arrange things, let's say. From my perspective, I don't care, you know, like if whatever, like pick whatever, like the point is that you pick at least two, right? So that you've got it in your mind and be consistent about it. You can also attend all of them. If you don't attend any, in a way that's your loss. Yeah, well, it's so in the end I would suggest that perhaps you can write one paragraph on the like modules you took, what you found interesting, what you okay, I started this and I did that and I finished it and it was nice, it was cool. Eric is the best teacher ever, or whatever. Like you can. But let me discuss this with the rest of the team.
Maybe about this, is the oral exam open book?
No,
Like,
oral exam will be.
Yeah, but like, I take notes. That's what I mean. Like, because I would take like, should write notes or paper.
Why would you need notes for an oral? It's not an exam. It's like, first of all, it's going to be about the essay, right? Like, so
Yeah,
you're
yeah.
going to present your work, and then we're going to discuss about questions, like what's going on, like that kind of thing. I mean, otherwise, before it was poster session, and then we were talking, like discussing with the students. That was also an oral, basically grading. But the problem there was that, yeah, it's basically a poster hall, like where everyone talks to everyone. Then you don't even know who's actually in the team in practice. So that's a bit complex. That's why we make it a bit more like structured and clean. Like that's it. Nothing to worry about. Like just like it's also not. Again, it's not to be pedantic or anything. We're gonna discuss about like what we showed them. That's why it's also good to be in the modules and like see how it went. Also in the project, how you experienced it, how you worked it out. Like what did you do personally? Like each person personally. Yes.
Do the modules have an assessment? Like
Yeah, that's what I was saying. Since the general consensus was no exam, there will be no assessment.
yeah, exactly. So you just follow the modules and you need to have 4 points.
Yeah.
But like nobody checks if you're really there.
No, like that was my initial idea when I was making the course in the first place. Then last year I had this feedback that, oh, it's too chaotic, like the way it's assessed or whatever. Like it's not that chaotic, but unclear. And now this year, like, no, we don't want structure. Okay, sure, but I still have to somehow assess, right?
Yeah.
Especially for the grades, it has to be 50% personalized. It cannot be that we don't grade teams, but we grade students. That's the main thing. As per UR, like the regulations. Other questions? Maybe a good idea is also if you maybe we can arrange that. Like maybe give feedback on what else, like what other module you would like to see, because in the in our institute we really have really top researchers. Well, not for everything per se, but for a lot of topics. So if you think like something is missing, perhaps yeah, why not like suggest it also. Yeah, maybe. Right. Regarding the essay, I would like to see it from the critical review perspective. So the way reviews for papers should be really like, you take a paper, you try to replicate it to some degree, of course, what is possible in a duration and with the resources. Reconstruct results, write about it, like explain the process, push it to the limits. Is it like really overclaiming, or can you actually generalize it? Like, explain it in nice graphics, perhaps in the form of a blog post. I think there is a template now, so you know, just like curiosity-driven, let's say, curiosity-driven studying here. Any other questions? Okay. So, okay, in this module, we're going to discuss deep generative models, and deep generative models are well, perhaps with ChatGPT, diffusion model, stable diffusion, DALLE, Midjourney. I've never used it. My wife has used it. Apparently, she has a lot of fun with it. Well, I never thought I would come to this stage this early, at least in my life. But yeah, well, anyways, the generative models are super popular now. It's impressive if you really think about where it was 10 years ago. Okay. Does this work? Right. All right. So in this module, we're going to discuss. We're going to discuss today about the like an introduction to generative models. I think you had one already, more or less, in deep learning 1, right? Or maybe in machine learning as well. Or did you do machine learning generative models? Not really.
No.
So the only place you did generative models was deep learning 1,
Yeah.
right? Then I'm going to discuss about deep autoregressive models, latent variable models, normalizing flows, energy-based models, and score-based and diffusion models. So 6 lectures, 3 credits, so half credit each. I'm going to share the slides, so you know we need to well, do what you want. No need to replicate necessarily. Right, so, and today we're going to discuss an introduction on generative models. So some concepts probably you already have seen, you know them. But still I would like to revisit them just to make sure that everyone is on the same page on one hand, and on the other hand, I would like to go step by step to understand some logic, some basic concepts. And what we're going to discuss today is, you know, what are generative models, using applications, like when or why would you use a generative model in the first place, a step-by-step minimum viable definition of a model for a generative model. Like, what do you need to have a generative model? Like, what is it exactly, like what are the thinking steps in the design process, in the modeling process, in the training process that you need? And I will also give a quick overview of the types of families of models. Right. Yeah. So, yeah, these are 2 examples of results of generative models. I will discuss a bit more in follow-up slides, but well, basically, these are selfies of Napoleon and Jesus taken. Yeah. Okay. Interesting. And this was what generative models could do in 2014. So basically, 9 years ago, a decade ago. So as a disclaimer, generative models, at least from my perspective, often sounds hard, and it is hard. It can be hard. I will try to have, you know, in this module, a first principles approach, because I think things like that, you know, like a first principles approach makes things simpler to understand. You know, what exactly is the problem, and if I know the problem, you know, why this solution? You know, like why not another solution, and so forth. So it will hopefully make the challenges look more natural, and the solutions also look more natural. So when things become too entangled, please ask me. Right? Or like stop me. Ideally, this module should be, again, during this course is more like tutorials in conferences. Like when you go to a conference, you've got like somebody presenting like some latest stuff. People ask, and you know there's a nice interaction. So please interrupt me and then discuss. I cannot promise that I will have always the answer right there, but I will keep notes. Like maybe I'll write in the blackboard, the whiteboard, I take a picture, and next time, or either in Piazza or next time, I come back with a question, the answer. Okay. In my opinion, once you understand the challenges, then it's pretty easy to easy. Like it's at least manageable to understand what's going on and the intuition behind solutions. So for generative models, basically, if I were to give an example, we want to design algorithms. We want to learn algorithms. Okay, so we've got learning algorithms. We don't just have algorithms. That paints new bicycles based on a few examples. So we give to the model a few examples. For instance, a few bicycles, or many examples. Actually, that's the trend now. You give them many bicycles, and then hopefully your algorithm can generate new bicycles. So bicycles that didn't exist. Well, of course, in this picture, I didn't generate a new one. I just took one existing from the web, but that's exactly the idea. It could have been a generated one. Of course, this also sounds a bit like graphics, right? Like in graphics, you also make pictures. What's the difference? Well, there are two very important differences. First of all, graphics is specifically for images. In generative models, you don't really. It's not just about images. It's about any type of data. Any type like it can be text, it can be sound, it can be multimodal. So it's not per se I want to paint pictures. It's more like I want to learn to generate the data that you feed me. If you give me images, if you feed me images, I want to be able to generate new images that look similar enough. And second of all, graphics is usually a deterministic process. Here, what we care about is probability density functions. So in that sense, this module relates to the probabilistic models from Wilker module. So in the end, we want to have probability density functions. And this probability density function is basically, learning it is basically the algorithm which will generate new images for me or new data. So in this module, I've got the computer vision background, so I always talk in the context of images, but do not take it literally. It can be any other types of data. Images is also easy because we can show pictures and everybody understands more or less what we're talking about. Okay. So we call them generative because once we have the probability distribution, so density function for continuous data, we can sample from it. If I have a Gaussian, I can ask, Python, NumPy, like run n, and then I generate a new Gaussian data points from my Gaussian, right? So imagine this, it would be a Gaussian, and then my data points would not just be single numbers, but huge matrices, and I could call it and then create new images. That's just the process. All right. Everything clear so far? Now, what's different from discriminative models? So basically, with discriminative models, we do we have a bit of a bit different modeling task. Given my input, given this image, with a discriminative model, I want to make a prediction. So is this a bicycle, or is it a cat, or is it a dog? Another type of task is, given this movie, this poster, this whatever, like reviews, can you predict the IMDb score? So usually discriminative models come with a specific task. I want to classify semantic classes in images. I want to translate one sentence to another, like English to German. I want to caption an image, so like if I give you an image, I want to be able to describe that this is a bicycle standing behind a white car and whatnot. AlphaGo whatever. Most algorithms, or a lot of successful algorithms, at least until very recently with ChatGPT, with DALLE and so forth, were discriminative because you simply want to solve a particular task. So generative versus discriminative models. Generative models learn the joint distribution x comma y. So you might not even need y, right? So y here is, for instance, classification label or IMDb score, whatever, like anything. Like you have like any random variable. The point is that you want to learn the joint distribution. So you want to learn to return likelihoods for all possible combinations between these two variables x and y, or z, or u, or whatever else. Whereas discriminative models need only to learn this green term, this conditional. So what is the likelihood for all different values of y given my input? I have my input already, and I want to make a prediction about for it. So, for instance, a discriminative model is about classification. Is this a bike? Is this image a bike or an airplane or whatever else? And ideally, my discriminative model returns a line which separates, like I fit an image to the line. So in the simple case, well, that's not a neural network, but in a simple case, my line is basically this weight vector, right? W1, WD. I feed it to my image. For simplicity, let's make it a vector, so not matrix or anything. It's inner product. It gives me a score. Is it like from this side of the line or from that side of the line? If this from this side of the line, then it's like belongs to one class, like a bicycle. If it's on the other side, it's not a bicycle. If you hide a regression task, I would be interested in the points on the line. Like it will be a regression task, so it would be like how much, how many wheels do I have, for instance, if I have a tricycle instead of a bicycle. Whereas for a generative model, you want to learn to return a number, a likelihood, a probability for all combinations. Is this like what's the likelihood for this image to be this image, so this x, so x is not the semantics, it's just the pixels. So what's the likelihood, the probability for these pixels to be showing a bicycle? Well, very low, right? Whereas here, the same probability is much higher. It's much more likely to be a bicycle. And in terms of like technical concepts, discriminative models basically do away from having to take the prior into account. Yes?
So basically generative models, if you have, I don't know, trained on a million objects, you're gonna get probabilities to a million objects.
Yes.
In a sense.
Well, infinite objects. Basically, let's say this is the real space times d for t dimensions. Basically, the generative model, assuming that it has infinite support, so it gives you like values everywhere, it will be able to give you a likelihood everywhere. So let's say a Gaussian has infinite support, right? Like it doesn't, you don't truncate it, right? So it goes forever. You can ask any point on the line, it will tell you what's the likelihood according to this probability distribution for that point, right? You can also ask for like any really, really large or really, really small number, it will always give you an answer. If your probability, for instance, if your probability is truncated, but between 0 and 1, for instance, it doesn't give you outside. It only gives you numbers, probabilities only for what is permissible. Okay. So, from a modeling perspective, as far as technical components go, generative models do not have to incorporate, do not have to learn, or do not require the prior, P of X. And this prior can be a very nasty thing, because basically you're asking what is the likelihood for all images here. Like, let's say for the task of, let's say we have a generative model which is not just about generating new images, but like this task. But finding the likelihood of an image, joint likelihood of an image and a label, semantic label. To be able to say whether this is a bicycle or not, like what the likelihood of this is a bicycle or not, the prior means that you have to learn all possible, all likelihoods for all possible images or possible inputs first, be it bicycles, cats, dogs, whatever, like dark images, light images, good illumination, shading, whatever, to be able to say something about whether this is a bicycle or not. Whereas when you've got the simple discriminative task, okay, is this a bicycle or not? You basically care if you find two wheels and that's it. You don't really need to care about what the world looks like per se, right? Do you understand the difference? Right. Like in a simple analogy, like to be able to speak a language, you don't need to learn everything about linguistics and how languages work. You just need to learn a language. You just speak and then you learn, and that's it. Right. What that said, generative models had in the past 2-3 years, since diffusion models appeared and score-based models appeared, tremendous successes, like unimaginable successes. Well, we've all heard ChatGPT. I'm curious to see how students will figure out ways to use it for their course. But yeah, to me, ChatGPT is impressive. That's a good question. Do you think it's impressive or not? Like, do you like it? What's your? I mean, you're literally studying AI when ChatGPT appeared, right? So, and it's not even ChatGPT is basically 3.5. So there was 3, there was 2.5, 2. There will be now there is 4. There will be 5. I didn't expect it. Okay, I honestly didn't expect this to happen. But what is your opinion? Like, do you like it? Do you find it impressive? Like, do you find it intriguing? What kind of intellectual or emotional reaction do you have to it? Are you afraid that it will dominate the world?
It's almost scary, right?
Sorry, yes.
Well, I find it interesting how it's very good at some things, like you don't expect it to be able to do, but then it's incredibly bad at other things, like it can't even count the number of words in a sentence.
Right.
And it's just like, if you can solve mathematical equations, you expect the model to be able to count words as well.
Right.
But it can't.
Yeah. Okay, good. It's almost scary.
Yeah, just how fast it's going.
Right.
Because we just had 3.5.
Yeah.
Now there's 4.
Yeah.
I've used 4 and it's way smarter.
Yeah.
We're better at doing stuff.
Right.
So yeah, with the developments right now and also the the modules coming soon and being able to work with images as well, it's going so incredibly fast.
Right. It is like, for me, that's in a way, well, it's good to be teaching again, like in front of real people. It is. Have you heard, do you know Ray Kurzweil, the singularity? That's fun, no? If you haven't, I got the book. It's not so great. It's very thick for the real information content, but there is something there, and definitely, brings memories. Yes.
I think I agree with you. The fact that it's happening too fast. We didn't expect this to happen in 2023, maybe.
Yeah.
Compared how it is going till 2022, and suddenly we get ChatGPT. Is the sudden jump is extremely scary.
Yes.
Big jump from what we are doing.
So the gradient is scary. It's not the actual function output, the function value, but the gradient of the function. Yeah, okay, that for sure. Basically, according to the singularity is that the technological progress goes exponentially, And at the moment we're basically.
We don't know where you are. Right?
Maybe we're at the start.
Yeah, maybe we're actually, yeah, you never know, right? It's of course that's just a hypothesis.
Yeah.
But you know, once you're like once the let's say intellect of the machine becomes equal to the intellect of a single human, then it's basically game over, because machines don't need to get rest, or you know, they multiply. They've got no weaknesses per se. Yes.
I also feel like it's very overhyped. Like,
Okay.
people are very much afraid that, oh, this is gonna take over the world.
Yeah.
Whereas, you know, I just I think read yesterday that in order to train ChatGPT, you need like 3 million per month to burn.
Yeah.
So the resources are just too immense. You need too much data to actually make it do something, and the expectations of people don't really match reality.
Right.
The counting words is a great example. I
Right.
think.
Right.
I also think that is also one example. I think we've already, we have gotten over the hype and we're calling it overhype. Like, we moved from that phase very quickly. Like,
Yeah.
we got surprised by it, and then we are like, the tech is too big, and now it's like it's not good enough for us.
Right. Yeah, that's true. Well, anyways, in the context of deep generative models, what I find impressive here is its generalization. I also don't think it's super accurate. I mean, it cannot be also super accurate. Like, it's like the more general an algorithm is, the less specific and accurate can it be for specific questions or for specific tasks. But it generalizes really well. So even if it does mistakes, it understands the question and gives like a reasonable answer, right? Like, not a correct answer, but an answer that, okay, it doesn't sound ridiculous, right? Like, you don't ask what's the time, and then it says like minus 32 temperature, like Celsius or whatever. And it generalizes in a really huge millions of prompts. So for me, that is really like the big difference. And this actually clarifies also what is AI. Have you ever thought, like, what is AI? Okay, is it just optimization? I mean, a lot of the concept we do is basically optimization. It's statistics. Well, ChatGPT actually, in my opinion, shows exactly what is AI. AI is truly about generalization and extrapolation. Can you actually have a machine that responds in very new inputs without collapsing? So I find this really impressive. In terms of actual modeling, because perhaps I'm more from a computer vision background, I find this more impressive. Like the fact that I can just give you like a sentence, and then it paints a picture. Like before, we couldn't even like have crisp images, right? Like you couldn't even have realistic images, and now not only you can have realistic images, but with whatever crazy prompts you ask it, whatever, like it paints a picture that actually makes sense. Of course, there is here the devil is in the details, because prompting here is very important. You need to have a very strong language model to provide the structure, the disentanglement, and then this makes everything much easier. But still, like, that is impressive, especially when you consider where we were 9 years ago. 2014 is when I finished my PhD technically. So not too far, like 9 years ago. Okay. Back then, grayscale images, like the faces data set, cropped, censored. Well, it's clearly a face, but yeah, okay. And now, in a few years, like it was getting better and better, clear mistakes, but still getting better. Now, extremely realistic images, to the degree that deepfakes are a potential problem, right? You saw the picture of the Pope with a white coat. That was funny. I didn't know that. Well, now whenever I see something absurd, like Donald Trump getting handcuffed, I say like, maybe it's like fake, fake news. But anyways, it gets really, really good, scarily good, at least for these types of data. In my opinion, for static data, it's like all this is static data. For static data, yeah, we're basically there. But about so for me, the next step will be dynamics and interaction and like causality. How do you put these generative models in the real world so that they understand what's going on? So, all right. Generative models are very impressive in what they can do right now. And of course, the goal of this module is to show how to do it yourself if you had 3 million euros to burn per month. I guess if you had, you could do better things with it, but okay, let's say you had it. The world as a distribution is an informative way of thinking about generative models. So let's say this is my data space, and these bullets are my data, my images. You can always assume that there is a probability, a true probability distribution, which is the red surface, that really, basically explains the data. So according to this, like the philosophy of probabilistic modeling, you assume that the data are generated from a probability distribution, like a density function, when you've got continuous data, or the probability mass function when you've got discrete data. So basically every image you see is a sample from this distribution. If it would be a Gaussian, it's a sample from a Gaussian distribution. If it's some other distribution, it's a sample from another distribution. Of course, having the true data distribution is literally impossible, right? Like, there is no book where you actually see, okay, like this is the distribution for images and this is the distribution for audio and whatnot. Like, that's something that it's theoretical. You assume that there is one, right? In fact, that's the modeling task. What is it? Like, you want to discover. So the red one is the true data distribution. What we do in generative models is we make an assumption. So what is the assumption here? Or what is one assumption here, like in this picture? Yeah, I think he was 1 millisecond faster, yes?
That the probability, the density function of the data is ellipse distribution.
Very good, yes. You had a different, okay. So the assumption here is that our distribution will be an ellipse. Okay, ellipse is a known shape, whatever, like I can manage it, like as a modeler. Much better, much easier than a weird arbitrary shape that exists in nature. And now my goal is to find the best possible ellipse that fits the data. The green one is, let's say, the best one. Of course, it's hand drawn here. So not literally the best, but okay, it looks close enough. This is another bad random one, whatever. So what are the possible things that we would need to consider here? What makes this a better one than this one? Like the green from the yellow, I mean, sorry?
Contained in it, I guess.
Right. So you want to have like best possible coverage, or in terms of probabilities, you would like to maximize the likelihood of all the data points under this distribution, correct? So if I assume, okay, I don't know what's my red one, literally don't know it, right? I only have my ellipse in my model. What is the best possible ellipse that would explain, like would give me the highest chances? So in probabilistic terms, if like that's your so X is my data set, X1, X2, so double to show that it's like a different image, not just like a dimension, X3, Xn. So what is my probability for my data set? Now, because this is a data set, and when I enter it here, so this is like what is the probability for all my images? 1. Of course, that's a bit complex, right? Like, because you have to consider all images at the same time. However, we assume that our data is identically independently distributed, IID assumption. So this whole probability is basically the product of individual probabilities. Right? So we decompose the task into what is the probability, the likelihood for each of the images, and would like their product, because they're identical, independently distributed, like to maximize it. So this is the data space, so the data perspective on the problem. From a modeling perspective, however, from a distribution perspective, from the distribution space, you got a dual view. This gray area is now the space, not of my data, but of my possible models. So one point is my green model. Another point is the yellow model. All other points are all other possible models. In fact, when you do SGD, you would like traverse this space to go discover the one that you pick in the end, right? And my true model, well, often is actually lies outside my model space. If it's in, I could hope to discover it. Like I could hope my model. So basically, if my red area would be a perfect ellipse, then I could design a model to fit the perfect ellipse, to find the perfect ellipse, right? So then this would mean that my red dot would be inside this area. If it's outside, the best possible I can do is find the model that is the closest possible to my true one. Okay? Is that clear? Yes?
Are assumptions reduce the model space?
Sorry?
Are assumptions about the world reduce the model space that we show this?
Well, the assumption is the model, let's say the inductive biases you add to the model. Like if you have, for instance, if you have a VA, we'll see later, with a Gaussian latent space, this describes all the VAs with this Gaussian latent space, like have latent spaces. If you have non-Gaussian, if your true data would have a non-Gaussian latent distribution, then it will be outside of this area. So the best possible would be to find the best Gaussian that approximates your true data, latent distribution. So, and this is literally what VAs do actually. So, if this would be your latent distribution, then you have to find the Gaussian that basically describes the best possible, like the closest match to your true distribution, and of course the closer the better, and like that's it. So basically, this area is constrained by the types of the type of definition you have for your model. If you have an autoregressive model, then it's really broad because you've got no constraints. But different types of generative models have their own advantages and disadvantages. Okay, we'll see them. We'll talk about it later. Other questions here? So this is the thing is an important realization to make when it comes to that's also more general like the journey for like deep learning. You've got the data, you've got the models, and hopefully your models are as close as possible to the reality. The only difference is that with generative models you literally try to find the true distribution or a surrogate of it, which is as close as possible. So then the task of discovering this probability distribution is very explicit. So you cannot circumvent it. Like with discriminative models, you can just ignore it. Here, you literally have to take it in, you have to understand the approximation you do. Yes?
How do you
Yeah, that's a great question. Well, we'll discuss this a bit later. But how do you think? Like, okay, so I'm asking because like that's the best way to understand things. Like, how would you let's say I'm telling you, okay, give me now. It's a distance, right? Like, let's start from the basics. It's a distance, right? So it can be anything.
You want to minimize that distance, so it would be like the loss. You want to minimize that process of optimization.
Exactly. So it can be a loss function, right? Like cross entropy, for instance, like which is basically maximum likelihood estimate. It can be Kullback-Leibler. In fact, it doesn't have to be distance. It has to be a metric, because distance has to be like also symmetric. KL is not symmetric. Basically, you need a function that tells you how close things are, and how close. Okay. Usually, it's in terms of parameters. Like if I take this set of parameters with another set of parameters, or if I take two functional forms, how two different functions, how close they are. Okay, we're going to see this later. Usually, it's the KL divergence. You've heard of it, right? That's a very standard choice. Okay, 2 more slides, and then we'll have a break. So, okay, why would you need generative models in the first place? You might want to do statistical inferences, right? So not everything is about giving one classification, like this is the car, this is not. Like maybe you want to say something about what what is the likelihood that this patient will have a heart disease in the next 5 years, or what are the chances that ChatGPT will dominate the world in the next half a year. So sometimes you want to be able to make statistical predictions, inferences, given your data beyond just like this one task. You might want to do sampling or generation, like some, just creating more images. Like that's fun enough. In my opinion, that's like a bit also. It's a good game, it's a good toy, but yeah, it's AI is not just about making you pictures. You might want to use it for representation learning. So basically, if I have an unstructured data space, how do I organize my data in a coherent and compact fashion, such that you obtain similar, codes for similar inputs, whatever similar means. You might want to use it for pre-training. For instance, if you have an additional tasks, like in reinforcement learning, you might want to have a world model that you learn something about the world, and then you add that to your model, to your reinforcement learning model, to make better predictions. You might want it for generalization, so to make sure that you don't overfit, because you have to basically explain all possible data. So hopefully you generalize better. You can use it also for some simulations, like physical simulations, which is perhaps quite close to something in generation. And why not learn distribution? Like you should not learn distributions just because it's cool, or because you might like the math, or it's fancy and whatnot, and use it when you have to use it, but you don't have to use it always. Things depend, like it depends on your modeling task. So as Vladimir Vapnik, do you know him? No. Well, let's say 15 years ago, when I started my PhD, like SVMs were the thing, and Vapnik was like the guy who made them. A very smart guy. Basically, his crux is that one should not try to solve the classification problem directly. I should solve the classification problem directly and never try to solve a more general problem, which is also a harder one as an intermediate step. So if I want to be able to classify images as bicycles, I don't have to learn what is an image and what is the world and what are all our possible objects. I just want to be able to say whether this is a bicycle or not. So learning the data, how it looks everywhere in the data space, can be very complex, can be very expensive. and more importantly, can be very unnecessary. So, if you want probabilities for inference, go for it. You want to learn things in an unsupervised manner? Well, go for it, or maybe not even quite, because self-supervised learning, there's the other module, is also a great alternative. Well, in the sense that it's also about representational learning, but without probabilities per se. If you want to generalize better and avoid overfitting, go for it. If you want to be able to generate new samples, well, you should definitely go for it, because that's the most straightforward way to do it. Go generative. But if you have a specific prediction task, and you have enough data, you have enough annotations, you want to get the job done, and like that's it, better go discriminative. No need to make things more complex. Okay, so let's have 10 minutes break until 9 o'clock and more. Well, 10 o'clock, and then we'll continue.
Sorry? You have there.
Oh, okay, yeah.
Deep learning. Die nog niet. Ik weet niet waar ik moet beginnen. Ja, zoals van de static point, toch? Ja, want die gaat er gewoon uit dat je in een beperkte space zit. Ja, dus die moet aangekocht worden wel. Of je zegt dat dat niet meer houdt. Zoals het er staat, houdt het niet. Nou, dat kan natuurlijk ook. Maar dan moet je een counter gaan zetten. Ja. Dat geeft een counter. Maar je dan gewoon zeggen, oh, ik heb hier een infinite space, dan vervolgens, oh, maar dit matcht niet met de assumptie dat we een beperkt.
Could it maybe be possible for you to share the slides before the lecture? Because then I can ride along.
Ah, all right. I'll do that.
Yeah. And also because I gave my preferences last Wednesday, but then some things changed. So I was wondering, like, because I don't really want to do my first pick anymore, but I want to do my second and my third. Is that still possible? Because okay, that's okay.
Okay.